Okay, thank you. Thank you everyone for showing up and welcome to Building Lightning Fast Apps with asyncio. My name is Asaf, and today I want to share a story about how we had a system in one of the companies I worked for, and the system had a problem at some point in production. The problem caused an outage, basically a complete outage. We will see that. The outage caused us to rethink of how we are designing the system and how are the components interacting. We'll share the thought process and everything that came up through that process, and then we'll reach the solution, what we actually chose when we had a working idea, and finally we'll show the learnings from this adventure of replacing a component and everything we learned. Right, so let's get to it. But before we do, a bit about me. My name is Asaf. I'm a principal software engineer at Sage. I worked at Dropbox, PayPal. In the last several years, I've worked mainly around distributed systems at scale, designed some of them, wrote some. And for the reasons you'll see, I really like asyncio. That's about me. And now back to the story. Right, so the first part is the problem. Why did we have to redesign a component or a system, subsystem? And to understand the issue that we had, we first have to understand the system. So this was a system like many other systems. It was an event processing system. Events were originating in the internet and reaching compute nodes. Those nodes took the raw events, computed whatever they needed to do, and produced payloads. The payloads were then forwarded to a load balancer. And from the load balancer, the events were dispersed around several gateway nodes. The gateway nodes sent the events to downstream systems. Now, the reason we had both compute nodes and gateway nodes is because we had to architecturally, for reasons I'm not going to really go into, but we had to separate things that were happening inside the network to things that were being sent outside the network. And those gateway nodes, as you can see, are basically Java nodes. They are Java services, but this was a Java service from a really legacy kind. It was an ancient service that the code was already kind of lost. We didn't have any access to the code, only configuration. However, we were told that this was an efficient implementation. It was lightweight, it was performant and fast, and there was basically no reason to replace it, even though we didn't like that we had a legacy system that we really can't see how it works. We were told it was good, and it worked, right? So we didn't have any compelling reason to replace it until we did. One day we had an incident. We had an issue in the downstream system. Some of the events sent to the downstream system produced an error. It looked like it was a random error that just was happening, and there was some logic in the gateway nodes that we really don't know what it was, because again, the code was obscure, but I mean, we didn't even have access to it. But maybe when there were too many errors, or there was a cooldown, or maybe an exponential backoff, the gateway nodes stopped sending events to the erroring endpoint. So we lost one node, and then we lost the other until we lost basically all of them. And that was, as you can see, a complete outage in a system that is measured and has only value when its events are reaching the downstream as fast as possible. So this was a huge loss of value for that system. And that was the compelling reason for us to kill that old service and build something new. That was the decision to build something new. But now, whenever you have to build something new, you have to think about how you're going to do it. So let's talk about how we drove the design process. First, we have to focus and distill the requirements. The first requirement is that the events and the workload is network bound. That means that we are mainly focusing on sending events downstream. It was the protocol that was used in that point was HTTP. The second thing is that we need low latency. The system is defined as an enrichment system. That means that its events needs to reach the other downstream systems as fast as possible, in less than a second. So we defined an internal SLO that since inception, 99% of events should reach the downstream within 300 milliseconds. The third requirement was high throughput. We had 150 million daily events at the time of the incident, and we were growing every year by at least 50%, so 50% every year, and that amount grew by 50% the next year. This was historically, that was the historical trend, and the 150 million events a day were not uniform, they were bursty, so we had to even deal with high burst and high peaks of events. The last thing is that this is a system where engineers, we don't want to build something that is too complex and hard to maintain. We wanted something that was easy to understand, that was evolvable, that was maintainable. So low complexity was a requirement, an internal requirement by us. And when you see those requirements and you see the low latency and you see the high throughput, a picture starts to emerge, a picture of multitasking. And before we go into how we solve the idea of multitasking, let's talk about it a bit. Right, so multitasking is when you have several tasks and you need to perform all of them. The general approach is to usually use some kind of queue. You put all the tasks in the queue, and then you consume the queue and perform the task. The naive way is to use it sequentially. You have some kind of worker that pulls the tasks task by task. Once it's done, it goes on to the next task and so on. Not hugely scalable. But in the second approach, the second common approach is to do this in parallel. We have several workers around several systems, around several machines or containers, and they pull messages. And whenever one is done, it pulls the next available task. So we can see that this was much faster, right? But we still have to ask ourselves: is this the fastest? Is this the fastest we can go? And to understand if that is the actual fastest way to do it, let's understand those tasks that we're talking about. Our tasks are network-bound tasks, as we said, and that means that these are HTTP requests, and they are IO-centric tasks. In this case, we'll analyze a typical task, an HTTP request. So the green part is the request, and it has three main parts. The first part is some kind of local compute. We are setting up the headers, the content, everything we need about maybe we gzip the contents, and then in the second part, we send the data down the socket and wait for some kind of response. When we get a response, the third part commences, and that's where we parse the response and produce some kind of output. Now, the first part takes some microseconds. The last part is also some microseconds. And the middle part, the one where we actually just wait, takes usually in the order of milliseconds, maybe 5 milliseconds, maybe 300 milliseconds, but milliseconds. And that's orders of magnitudes more than the microseconds, in which we're just simply waiting. We're not really doing anything. We're just waiting for something to wake up. And that means that for these types of tasks, more than 99% of the time, we're just waiting. We're doing nothing. And with that understanding, we'll have a fresh look at our multitasking. If we look at the tasks now, we see that they're mostly hollow, right? They're IO tasks, so that there is some kind of work at the beginning, some work at the end, but the middle part is fairly empty. And if we look at this chunk of time between the three workers, no work is actually getting done. Everyone's waiting. Not very efficient. We might think of another way to handle these IO tasks. Again, we have 4 HTTP requests, 4 tasks, and we are putting them in a queue. In our case now, the worker is a single-threaded worker, and it works like this. It pulls the task from the queue, and it processes it until there's nothing more to process. We have to wait for something to return, in this case, the network. So we put the task aside and we handle the next task, the green one. And we do that again and again until there are no more tasks in the queue. Now we have to wait, right? So wait until something wakes up. In this case, it was blue. It woke up first. So blue is back. We process blue. And while we were processing blue, the yellow task already finished. It also is waiting for us to process it. So we take that, we process it. And again, nothing else has returned. So wait some more. Then the green one is back, and then the red, and time. We're done. This is also very fast, very efficient. There was little to no dead time that was inefficiently used, because while we were waiting, there were no other tasks that we could have completed. So we were at maximum efficiency. And also we were in a single thread. So we have two ways of looking about it. One is that it's like juggling, right? We have several tasks somewhere in the air. That means that they're waiting. So we have items in our hands that we can juggle and manage. And when those go in the air, other balls will fall down, we'll catch them, and we'll do something that we need to do with those items. The second thing that we need to see here is that this is a single threaded execution. That means there are no locks, there are no mutexes, no weird concurrency or parallelism structures. It was just plain old synchronous code. And that's a great benefit. No locking, no thinking about race conditions, very convenient. And that is the basis of what we call the event loop. If you've heard about async IO and unblocking IO and concurrency, you've heard about the event loop in several occasions, I'm sure. And let's explore the event loop, right? So we have the task queue and we have the loop, which has four parts. We have the queue, we have the compute, we have the await, and we have the poll. So first, we take a task and we queue it. Then we compute whatever we can compute locally. Then we await. Once there is nothing else that we can do, we just have to wait for something to be back. Maybe it's network, maybe it's disk, could be anything. That is IO bound. And then once we are awaiting, the task goes to the awaiting task pool. There's just some kind of structure or container that holds those tasks that are waiting. And if something wakes up, we need to take it back to the task queue and continue. If nothing wakes up, we can still pull the task queue and the awaiting task until something wakes up. Why do we pull the task queue? Because some other thread might be adding tasks to the task queue, or some other task is spawning new tasks. Now, this is the conceptual implementation here, the conceptual structure. It's generally the same for all implementation, but there might be OS specific details that are a bit different, but they don't change the same that concept that we're talking about. And let's see how that looks like in code, right? We have import async IO. This is the library that we're talking about. It's in the Python standard library since Python 3.4, and we have two what we call coroutines. They're the same as functions, but they have the async def keyword, and that means that they are routines or functions that run on the loop, that interact with that event loop. With this one, foo prints foo, then we sleep for a second on the loop, and then we print /foo. Now, when we sleep, we do the await. We have the await keyword in front of it, and that's very important. That means that the await is the sleep is happening on the loop instead of just being spawned as some kind of task and then just withering away. So we have to use the await, otherwise it will return immediately and will not have this interleaving. The second coroutine is called bar. It's generally the same. It has bar and then it sleeps for 300 milliseconds, but this is a synchronous sleep, time.sleep, the regular one. And then there is an async IO sleep, 500 milliseconds of sleep, and then /bar. Now, the time.sleep here is going to behave like any other compute-centric code, like any other synchronous code that takes 300 milliseconds to complete. There is no interaction with the loop whatsoever in this sleep. So we're not gaining any benefits from the concurrency. The other sleep, the await sleep, does. And the last part here is to actually register those tasks on the queue, and in the loop. So we have coroutine called main, and main calls async IO.gather on foo and on bar. Now we are going to basically ignore that those await, the async def main and the await, the task that it produces, because there's just boilerplate. We're just going to focus on foo and bar in the next one. So then run async IO.run main, and we'll see how that works, right? So we have the code on the left. By the way, this code is going to compile and work if you paste it somewhere else. So if you want to play with the code, feel free to. We have the loop, and then we have the console on the side to see how the prints go. So first, as we said, we're only focusing on foo and bar. We add foo and we add bar to the queue. First thing, we're going to take foo. We're going to do the queue foo, and we will compute whatever we can. This is print foo, and then we have to await. So foo is awaiting. It's in the await pool. we dequeue the next task because the foo is not ready yet. And this is bar, so we print bar and we do time.sleep. So we just sleep, nothing is happening for 300 milliseconds. And then we just go to the await part and bar sleeps for half a second. Now both tasks are in the waiting stage and something's going to wake up first. And who's going to wake up first? Well, if you said bar, you're correct. After half a second, bar will wake up. So bar has woken up. It goes back to the queue, gets dequeued. We print /bar, and bar is done. And well, now we're waiting for foo. And how long will it take for foo to wake up? If you said 200 milliseconds, you're right, because we waited already 800 milliseconds for bar, and foo is waiting for 1 second. So there's 200 milliseconds of delta that we're still waiting for. After 200 milliseconds, foo is waking up, gets dequeued, and we're computing the whatever is left, that's print /foo, and then we are done with foo as well. And you can see that the prints are foo bar and then /bar/foo. The prints are not in order for how in relation to how the tasks started, but every task finished from top to bottom. It's just that the tasks were interleaved. While one task was waiting, we could execute on the other task. And that's why how you can see that bar ended before foo did, even though foo started before bar. And now that we understand how asyncio loops or event loops in general, how they work, we can see how we designed the solution. So this is the system that we spoke about before. You remember the system. We have that part that we want to replace, and let's zoom in on that. We have a load balancer on the left side, we have the downstream on the other side, and we have the service in the middle. So first, we took the load balancer and replaced that with the distributed queue because that lends itself very well to asynchronous workloads. We had a consumer reading from the queue, that is the new service. And the consumer fed another process within itself that was basically just a loop. And the loop was concurrently executing those tasks, so it could execute a lot of tasks in the same time. But this is single-threaded, right? There's only one core being used for the loop. And those machines that were running the service had many cores. So how do we gain better utilization? We create several event loops. We added more processes through the multiprocessing package, and the consumer fed all the processes through a queue, internal IPC queue, and then we could reach higher throughputs for every instance. And when we think about this replacement that was replacing a cluster of Java services, in that case, our original Java cluster had 8 instances. How many instances of the new service will we need to match the same level of performance as those 8 services? How many did we need to deploy in production? So we did some load testing and benchmarking and number crunching, and we reached the conclusion that we only needed one instance of the new design was enough to outperform the entire Java cluster of 8 lightweight, fast, performant Java services. So with that understanding, let's see how our solution looks like. We are removing the old parts and we're putting the queue and a few of those Gateway 2.0 nodes. We put a few not because we need that for performance, but because this is production and we expected some issues or outages, and we had to make sure that we are able to survive and be resilient through those challenges. To be fair, it was very rare and the system was extremely stable, and it still is extremely stable. So there's no real challenges there in terms of maintenance. However, since this is still production, we are keeping a few instances in production. With that solution, we can say that everyone's happy and the system is extremely well performing. The learnings. What did we learn from this adventure? First, we thought, we're asking ourselves, is asyncio now the answer for all our multitasking needs? Is it a silver bullet? Is it even better than multi-threading? Well, let's see. When we look at non-IO bound tasks like compute tasks. These can be many tasks, like it can be parsing JSON or hashing some blob or computing ML models that have no IO, they just compute, or even opening a file synchronously and the old API that doesn't interact with the loop. All these tasks have no interaction with the loop, and most of them, apart from the open file, there's no dead time in them. There's no idle time in there. We're not waiting for anything. We're 100% busy. The CPU is working as fast as it can to finish the workload. So for these tasks, if we try to interleave them on a loop, we'll just end up running them sequentially. So these tasks are not suitable for an event loop. There is no performance gain to be had from these tasks as coroutines. So no, it's not superior to multi-threading. It doesn't replace multi-threading. It's another tool in the toolbox. Multi-threading is a tool. We have many tools that we learned and collected along the way. asyncio is one of them, and it's a very useful one. So it's great to have it. The second thing is that we saw that, okay, we have concurrency and we want to maybe just design our systems for as high concurrency as possible and neglect parallelism, which is a bit different. And we saw that in our solution, no, we use concurrency per service, per process, per event loop, but we also use many event loops in parallel to reach even higher performance. So we can say that concurrency and parallelism, in this case, complement each other. With those understandings, we were able to build what we call the ecosystem 2.0, the next generation. We replaced many parts with new implementations that contain the async IO. Even the compute nodes are now containing async IO. They're more parallel and they're more compute heavy, but there are still parts in them that can benefit from async IO, so they have that in them. And the system that was handling 150 million events daily was able, on the same hardware, after a couple of years, to reach over 1 billion daily events, and it's still growing, and the system is still stable on the same hardware. So that was a great achievement. We were super happy with what asyncio was able to enable for us. The grand takeaway from this is that for every organization, for every team, there might be some systems that are legacy or old or might benefit from some injection of performance. So go ahead, analyze, see if something can benefit from moving to an asynchronous or concurrent workload. Once you do, be brave enough to experiment, to change, to try and benchmark and see if that works for you, if that's the right solution for you. And if it does, integrate it. We for sure learned that this was mature enough to be and stable enough to be in production. There's many async-based connectors to almost all infrastructure that you can think of, from databases to HTTP services to queues, whatever you can think of. And if something is missing, contribute some open source. I think everyone will benefit from that. And that is it. Thank you for listening. I hope you enjoyed the story, learned something new about async IO and concurrency in general. And this is my LinkedIn. If you want to message, give some feedback, ask questions, whatever, it's here. And if you have any questions, I'll be happy to take them.